Okay, so thank you very much. It's a pleasure to be here. It's my first time here, so I want to thank everybody for organizing. I'm enjoying it very, very much. So the theme of this talk is basically to try to relate the glass transition, which is typically regarded as a transition which is very, very different from conventional melting, in which you have topological defects which actually can, of course, induce melting, to actually try to relate the two, basically to say that the glass transition, or more precisely, the onset of glassy dynamics might be in disguise a melting transition in which topological defects appear and so on, but not in an obvious way. So this is, of course, what I just alluded to, that you have, as of course you know, and some of you, of course, worked on, that you can actually have transitions in which you have proliferation of topological defects, whether it be vortices, dislocations, discriminations, grain boundaries, and so on, which can induce melting. Okay, so this, of course, I guess you'll, of course, know. And let me tell you about what the problem is. What is the glass transition problem? This is a very, very old problem. And of course, if there are any questions, please stop me and ask questions. So this is a very, very old problem. And the problem really is the following. You take any fluid you want to think about, at least insofar as we know, any conventional fluid. Okay? So we're not talking about helium here, but sort of any conventional fluid. And if you cool it down slowly under ambient pressure, it becomes a solid. Okay? On the other hand, if you cool it down fast enough, and of course what enough stands for depends from material to material, but if you cool it down fast enough, it does not crystallize, and it has a higher viscosity. It's a so-called supercooled fluid. It's supercooled below its melting temperature, and at some stage, the viscosity becomes so high that it's called the glass. When viscosity exceeds a threshold value, which is a bit arbitrary, 10 to the 12 Pascal seconds, people just call it the glass. Okay? Now the problem really is that even though we get to this material, this phase in which viscosity is tremendous, and it seems to be a solid and all for many practical purposes, nothing really happens dynamically. So if you look at heat capacity measurements and so on, there's nothing really there. You might see a small blip here and there and so on, but the changes that you actually see are not profound. By contrast, if you look at the dynamics changes dramatically. The viscosity ultimately shoots up by orders of magnitude. It's not uncommon to actually have shifts of viscosity in like section time scales by 12 order of magnitude or 15 order of magnitude over a relatively narrow temperature range. So dynamics increases precipitously, but on the other hand, thermodynamics doesn't change that much. And of course, as I guess you all know, the structure of these materials is pretty amorphous. You can actually find short-range orders and so on, but it's nothing like a crystal, of course. This is very much unlike conventional transitions in which dynamics and thermodynamics go hand in hand. Here, dynamics do one thing, there's a tremendous change, but thermodynamically, nothing profound really happens. And that's a problem. How can this be? What's going on here? Okay. So basically, as I just alluded to and so on, so you can have a huge change in relaxation times, but there's nothing really profound dynamically. So if it's a transition of any type, and people do call it quite often a transition, it's certainly not of a Landau type. That's the conventional wisdom. So these are some works we actually, when we worked on this, so I just mentioned my former student. Oh, I apologize. I apologize. So Nick Weingartner, he was my former student. He just graduated. This was work done with Flavio Nogueira. So he's a little field theorist. Ken Kelton is an experimentalist in our department. And these are my principal collaborators on this. Okay, so before I run out of time, and I will run out of time pretty soon, let me tell you what conclusions really are. So conclusions sort of are, but if you think about this problem, which seems to be classical, and of course we might say sort of silly to think about this problem quantum mechanically. Nonetheless, if you think about this problem quantum mechanically, think about terms of eigenstates and so on, in a very, very simple setting that I described to you, then that approach suggests that there might be an underlying universality in which the only important energy scale in the problem is that of equilibrium transitions, in which you have topological defects, the usual type of melting. Okay? That's the basic conclusions from this theory, which of course has consequences if it's of course correct. So, as I just alluded to, basically, the idea is that you have a melting of some type, but it's not obviously usual melting. Otherwise, of course, you would have all the usual hallmarks of conventional melting transitions, but it's sort of a rounded off melting transition, okay? And nonetheless, the only important temperature scale in the problem is that of equilibrium melting. So here's a prediction of the theory. So according to this theory, as I just alluded to by now 4 times, the only important temperature scale is that of melting, or as people called the ubiquitous temperature for when you have supercooled fluids. I apologize, I'm going too fast here. So that means that you can actually, if it's indeed true, you can actually scale the viscosity data, which is drawn here on the horizontal, on the vertical axis. So the viscosity that you measure for supercooled fluid at the temperature T, you divide that by the viscosity measured at the melting transition, at equilibrium melting, for the same supercooled fluid. And you plot this as a function of a dimensional quantity, which is how far below you are relative to equilibrium melting. Okay, there's only one dimensional parameter here, which is a bar, which varies from fluid to fluid, but doesn't vary that much. It's of order typically of 0.07 numerically. And as you can sort of see here, regardless of a figure I'm going to try to describe to you, the figure might be wrong, it might be right, but regardless, it's sort of a fact of nature. But all these different fluids that actually are plotted here, they collapse into one universal curve. So that strongly suggests that in whatever mechanism really is, the important temperature in the scale in the problem is really that of equilibrium melting. Otherwise, why would 45 different fluids collapse here onto one universal curve? And as I'll show you momentarily, you actually have even more fluids that can collapse. So here, for instance, we have 66 different fluids that can actually collapse onto one universal curve. So here's another rendition of the same thing. Here are 66 different fluids on the same curve. And here we have both the viscosity data and also other measurements of relaxation data, like what you have from electric response and other quantities. So you see that there are some outliers, of course, as you see here and so on. But by and large, all these different fluids, 66 different fluids that we can actually could find data on in the literature, they all collapse into one universal curve, with the only temperature scale which is really important, as I now say for end of time, being that of a melting transition. So, as I alluded to earlier, glasses are ubiquitous. So you can, of course, have them in ordinary window glasses. Yeah. I'll tell you a moment later on. Yeah. The Vogel filter has more parameters. Here there's actually, and it doesn't assume melting. Here only temperature scale is actually that of melting. So any fluid, as far as we know at least, it can be made into a glass under the right conditions. So basically you just have to quench it in an appropriate way. So by any fluid, as I mentioned earlier, you can think about window glasses, silicate glasses, which have of course been known for millennia. Think about all sorts of many organic fluids. You can think about metallic fluids. So metallic glasses are actually quite hot and so on. Also, you can think about many electronic fluids that actually exhibit the hallmarks of very, very slow dynamics, as you have an NMR wipeout and other signatures and so on. So basically, the key point is that any of this, as far as we know, any disorder-free fluid, if you cool it down fast enough, it can become into a glass. Okay, as I told you earlier, how fast you have to do it depends on the material. But in principle, any fluid can become glassy. So it's a universal phenomenon. And here is an example of this universality in your kitchen. So you can take basically a plastic bottle and fill it up with water, but water really has to be pure water. But no impurities are there, otherwise it would crystallize. So fill it up with water. Take that bottle, put it in the freezer, and wait for about an hour, okay? And after an hour, open the freezer and take it out very, very gently out of the freezer. So don't perturb it in any particular way. Take it out very, very gently, and pour it into a glass or a container. And as you pour it down and the water strikes the surface, it will start to crystallize. As you pour it down more and more, you'll have this column of ice that develops. Okay, so what happened here is you have water, which becomes which is supercooled, and actually it crystallizes because upon striking the container surface, actually there's enough energy that it actually has to trigger and start a nucleation process, which proceeds. Okay, if you perturb it a little bit, it will actually crystallize. So actually, you can see videos of this on YouTube. People try it over and over again. It's not easy to actually do because usually there's some perturbations that you actually have. But if you do it in the proper way, this is actually what will happen. And then not only water, any material in principle can be supercooled. Because this is a universal phenomenon, there have of course been many, many theories trying to explain this universal phenomena, which a subset is sort of alluded to here. Okay, so these are many of the, and currently the one that's sort of most in fashion is this random first order theory. Okay, but many of these ideas, many of these theories have very natural ideas. For instance, if you think about so-called dynamic facilitation, the idea there is that you think about a subway, that you want to get out of the subway. In order to actually be able to move, other people have to get out of your path. So you have to have some correlated motion. And of course, that motion can become inhibited when there's not much way to move. So you can have very useful dynamics by result of governing laws of how you can actually move.
So what's the role of purity for very pure water to have this thing work in the YouTube thing?
So it would just start the nucleation site.
So within that 1 hour, it's like a fridge. It's gonna.
It will be just ice. You'll take it at just ice. If you stay longer, typically it will just be also a bottle of ice. But yeah, if it's pure water and you do it right and don't perturb it, it will do just that. And so, and of course many other theories, okay? And all of these different theories, they contain multiple parameters. And in particular, as far as what I want to emphasize here, these parameters are different from that of conventional melting. So it's always assumed to be that whatever it is that underlies this phenomenon is radically different from usual melting. Okay? But as I showed you earlier, for whatever reason it actually is, it seems to be that you can actually collapse the data of the viscosity and other relaxation data that you can actually find in the literature onto universal curves. Okay? So it seems to be that actually the two things are related. So the conventional picture people have, literally and figuratively, is that of an energy landscape. So you think about high-dimensional space in which you have many, many different degrees of freedom. And you can think about starting in some particular place. And you want to make your way slowly, or not so slowly, ideally, into the true ideal ground state or the low energy state. But of course, you have problems because you have to surmount barriers in order to go from one place to the other. And that's the origin, as people discuss for a very long time, in very different contexts, of course, also proton folding and so on, of why glassy dynamics actually onsets. Okay? This is another cartoon of the same thing. So you want to go from one basin to another basin, but of course that's not trivial because you have to do it many, many times, and you have to overcome barriers and so on. Hence, the dynamics is slow. So this is another common cartoon you will find in many papers. And this cartoon, as you can sort of see here on the vertical axis, I apologize. On the vertical axis is energy itself, okay? On the horizontal axis is some generalized hypothetical coordinate that you think about. And of course, this is the high-dimensional, it should be a high-dimensional cartoon, but here we only draw a particular small cross-section of it, okay? And you can actually think about achieving the ideal crystalline state, which appears here, okay? But you can also very readily get stuck in these small basins that are everywhere here. And at low enough temperatures, you can actually go into this so-called ideal glass state. That's the conventional wisdom. In most, this is not by everybody, but that's what most people actually believe occurs. Now, you asked earlier about Vogel filter, and earlier also alluded also to fragility yesterday, very, very briefly, when talking about Vogel filter and so on. So this is a copy of it from a very, very famous paper, influential paper from 22 years ago by Austin Angel, in which you cannot read it, nor can I, but here are very disparate fluids. And what's plotted here is the log of the viscosity divided by viscosity at the glass temperature when the viscosity becomes 10 to the 12 Pascal seconds as a function of this reduced temperature, which is Tg, the temperature which is the system becomes the glass, divided by the temperature itself, okay? as you can see, of course, some fluids don't deviate a lot from a straight line. A straight line here on a log scale means activated behavior. It's Arrhenius behavior. It means that the temperature scale, the viscosity goes like e to the power of some energy scale divided by temperature. Okay? So we want just one of our temperature, which is of course what appears here. The log, that's not surprising. Some fluids, like the silicates, don't deviate from a straight line by a large margin, and they're called strong because it's assumed to be that the structural, that they actually equilibrium doesn't change that much, and that's why the energy barriers are sort of constant, and that's why nothing really changed dramatically. On the other hand, some fluids, like this one, ultraphenol, you can sort of see here that I have 5 minutes left? Sorry. Okay, sorry. You can sort of see here that the viscosity shoots up by many order of magnitude, so by 60 by 15 order of magnitude, and going from this point here to all the way up to the top scale over a narrow temperature range. These are called fragile fluids. Okay, they're not strong, hence they're called fragile. And the most common fit people have for this, as asked earlier, is the so-called Vogel-Fulcher law. This law was introduced empirically with no theory 95 years ago, as you can sort of see in these papers. I apologize. And as you can sort of see here, if you believe this form, so basically what this says is that the increase in the viscosity is faster than Arrhenius. It's not e to the power of some constant divided by temperature, but e to the power of a constant divided by temperature minus another temperature, T naught. Okay, so it increases more rapidly than it would have been if it was simple activated behavior. And of course, what this implies, if you believe this form, that there's some essential singularity that occurs at this temperature, T is equal to T0, T is equal to T naught. And that's presumed to be this ideal transition to the glass. What I showed you in this cartoon, that you have this ideal glass. So what people actually believe is associated with that. And most theories try to derive this form. Okay, and in this form, you can sort of see that you have 3 or at best 2 parameters. You have this prefactor here, this eta naught. You have this constant D. You have this temperature T naught at which divergence occur. And nowhere here in this form is there any relation to equilibrium melting. It's assumed to be completely different. Now, my approach is actually is quite different. And you might say naive and sort of silly and so on. But we'll try to solve it as a homework problem in quantum mechanics. And so we'll try to write down the many-body Hamiltonian, which, of course, we can all write down, but none of us, of course, can solve. But let's write it down nonetheless. So let's imagine we write down the Hamiltonian for many-body systems, including nuclei, electrons, and so on, Coulomb interactions, spin-over interactions if you want to add them in, and so on. And of course, this is a theory of everything for us, in some sense. But of course, you might say it's useless because we cannot solve it. And you'd be absolutely correct. It would be typically, of course, useless to do. But it's not as useless as you might believe to be. And the important thing here, I should emphasize, that this is, in sort of a French rendition, this is a true glass, a real glass, in the sense that the coupling constants and the Hamiltonian that you see here, the real Hamiltonian, there's no disorder. The masses are just what they are. The interactions are what they are. There are no coupling constants here which are random. It's not a spin glass. Even though glasses look disordered and so on, the underlying Hamiltonian that describes the systems is uniform. There's no imposed points disorder. So in principle, of course, we cannot do this, but in principle, there exists a complete set of eigenstates. So let's imagine we label these eigenstates, I apologize, these eigenstates by here, phi n, and we can write down, we can sort of plot the spectrum. Of course, the spectrum is not ideally, like in harmonic oscillator, like here, it's not equally spaced, of course. As you go to higher energies, of course, it becomes more and more dense. Entropy goes up. But nonetheless, you have some spectrum, of course, from this problem. And associated with that, you, of course, have these eigenfunctions phi n. Now, here is, when I to come, I'm sort of claiming that all of these energy states here, these eigenstates here, at high enough energy densities, they correspond to the eigenstates that have a fluid-type features. Even if I cannot solve this problem, I cannot diagnose a Hamiltonian, I can sort of assert that at high enough energies, all these eigenstates have fluid-type characteristics. At low enough energy densities, all these eigenstates have solid-type characteristics. And there's some intermediate range in energy densities in which eigenstates have mixed properties of both the solid and the fluid. Now, why do I say that? I can say that because we know that typically in more than 2 dimensions for conventional systems, at high temperatures, we have a fluid. At low temperatures, we have a solid. And if we actually use any ensemble, like for instance, a micromechanical ensemble, and look at any observable O, we can write down the expression value of O at an energy E in this ensemble as the average value that you have of the expression value of O over all eigenstates phi n that lie in some energy window of arbitrary width delta E. The important thing about delta is it doesn't scale with system size. It can be as large or as small as you want, but it doesn't scale with system size. And in fact, recently, in the last 10 years or so, people have been asking themselves what happens if you take delta E to be equal to 0 regarding the so-called eigenstate formalization hypothesis. We don't do this here, but basically this is, of course, what describes, as you all know, micromechanical ensemble. Any system in equilibrium, if it's not of too long range and so on, not pathological, what you actually measure in equilibrium will be equal to what you actually calculate here using this sum. Now, typically what we do is we evaluate the sum for some system we can actually solve, like an ideal gas, harmonic oscillators, and so on. We get an answer. Here, of course, we can't do that because we don't know what the eigenstates really are. We cannot write them down. It's useless in some sense. But here we can actually use empirics. So empirically, we know for this Hamilton I just wrote down for you earlier, the sphere of everything, empirically we know that all these systems can be equilibrated if we don't actually quench them. By which I mean that if you actually measure them in equilibrium, what you actually measure for any quantity O you want to think about will correspond to this average. Okay, so this gives us sort of a dictionary. By looking at what happens to eigenstates, we cannot actually calculate relative to what we have from empirical observations. Okay? Now we know at high enough energy densities, when we're in a fluid phase, empirically, what we measure corresponds to a fluid phase, meaning that the eigenstates here at these energy densities, which are high enough, they exhibit features on average, because this is an average that I have here, on average corresponding to a fluid. And similarly, if I go to low enough energy densities, what I actually measure will be that of a solid. Is this clear? So this is this cartoon. So if I go to high enough energy densities up here, I will have eigenstates that on average correspond to the fluid. If I go to low energy densities here, I'll have eigenstates that on average correspond to that of a solid. And if I have latent heat, I will have eigenstates in that interval which will have mixed properties of both the fluid and the solid. Okay? Okay, and I should, of course, mention that so whatever you want to think about, phonons, topological defects, and so on, dislocations is an example, of course. All of these things that actually you can think about associating with solid-type eigenstates, they all appear here. Okay. So if we believe, as we typically do believe, that crystals don't break any symmetries apart from the conventional ones, like translations, rotations, and so on, then that means that at low energy densities, that in the full spectrum that we actually have, the one that I have here, all of these eigenstates that I have here at low energy densities, if I look at all possible, they all correspond to crystalline eigenstates. Okay? Nothing else can appear because I would have other eigenstates of a different character. I would have additional symmetries. I would actually have to break additional symmetries to actually get the crystal. Okay, so that means I can actually, crystalline eigenstates they span completely the Hilbert space that I have at low energies. So now let's do a thought experiment. Suppose I start now at high temperatures and I cool the system down very, very quickly. Okay, so I start off with some initial state. So this is psi initial. Psi initial corresponds to something which is close to an eigenstate, because if we're not close to an eigenstate, I would have a mixture of different energy densities, and I would actually get what I would compute in various ensembles. And then I cool down. So I cool down, I change my Hamiltonian in some particular way. It doesn't matter how I do it. Energy goes down because whatever I do to it does not commute with Hamiltonian. And the final energy density is actually now lower from what I had initially. Now, regardless of what I actually do, at the end of the day, I have a new state, psi, which I can actually expand in a complete eigenbasis of my Hamiltonian. Okay? Now, as I told you earlier, we obviously cannot calculate what these eigenstates really are, but we do know, as I just described to you in the last few minutes, that these states phi n, if I go to energy densities which are high enough, they correspond to the fluid. If I go to energy densities which are low enough, they correspond to that of a solid. Okay, so now, and I can do the same thing if I have an open system and so on, so I can do this anyway. This is sort of a general feature. So now if I want to calculate the probability of having different energy densities, that corresponds to this sum here. This is a probability that temperature T, final temperature T, I have an energy E. So it's basically, of course, the sum of the moduli squared that I have of all states that have an energy E. Yeah. Yeah, so you can do it in a variety of ways. So this, you can think about also the unitary operator in some ways. But the unitary operator obviously does not commute with the Hamiltonian, because if it were to commute with Hamiltonian, of course, energy would not change. So whatever I have here, this H twiddle, doesn't commute with H. So energy goes down. Energy is measured by the Hamiltonian itself, H, goes down because this H twiddle doesn't commute with H itself. So I can think about the system plus its environment as one big system, and which is a closed system, and I can write it in this way. But it doesn't really matter. Whatever I actually do with my system, I can write on my full state in the eigenbasis spanned by all these eigenstates that I have in the Hamiltonian, because they form a complete set of states. Okay, so as I just mentioned, in this sum here, in this probability that I have here of finding different states of various energies, some energies will correspond to that, some states will correspond to that of a solid, if very energy is lower than that of a system at melting, and some will correspond to that of fluid. So here in general, I have a mixture. Okay, so when I decompose my state in the eigenbasis of Hamiltonian, I have a mixture of states which are partially fluid and partially solid. So here is a cartoon of what actually happens. So imagine I start off initially at high temperatures somewhere up here, okay, somewhere in these eigenstates right here. I cool down very, very quickly. Because I do it not adiabatically, I do it very, very quickly. I don't stay close to any eigenstate, and in general I will have some spreading. Okay, so as I cool down, I will have the distribution I just alluded to of a probability of finding different energies E will look something like this. So we'll span both states, high energies, and states at low energies. So we'll have both a component which behaves like a fluid and the component which behaves like a solid. As I cool down more and more and more, the center of mass of this distribution, so to speak, goes down. Okay, so overall, the average energy density goes down. But in general, there'll always be some finite probability of having arbitrary high energy there. Okay? Now, of course, you can calculate whatever you want to measure. So you can calculate the energy itself. That's, of course, easy to do. And you can, and from that, you can, of course, calculate any quantity like heat capacity and so on. And you can also calculate slightly more involved quantities, like, for instance, the viscosity in a very, very simple way. So if you consider any quantity all you want to think about, and look at its long time average. So LTA here stands for the long time average of any observable O. What does it correspond to? By definition, it corresponds to the value of O that you have at time t prime from the initial time to the final time, and you make this window of times arbitrary or large, and you average over it. Now, again, you can write down these states that I have here, this psi of t's. You can write down them in the complete eigenbasis of the Hamiltonian. So you have these amplitudes here. Okay, and so what you have ultimately, as you can sort of see, and this is, of course, the conventional calculation, it's very, very simple, is just the matrix element you have of your observable between different eigenstates of the Hamiltonian, multiplied by these amplitudes of being in these different states, multiplied, crucially, by this integral that I have over time of e to the power I, the energy that I have in state n, minus energy that I have of state m, times t prime over h bar. Now, as I look at the long time average, when I take this time here to be infinite, this integral will become the delta function. So basically enforces that En is equal to Em. So ultimately what I have are just diagonal elements. So the long time average I have with any quantity ultimately just corresponds to a sum of diagonal elements. Okay? So I can write this down as a sum of diagonal elements. So basically it just corresponds to probability being in different states, okay, times what actually I will measure in those states. Now, I can convert this, of course, into this integral over these energies I told you about earlier, this probability distribution I had told you earlier, of having this Pt of E, the probability of being at state E, at temperature T, at the end. This is just basically just writing down what these are in a continuum, multiplied by the average value of O in equilibrium. Because remember, the average value of O over eigenstates over a narrow energy window just is nothing else but the equilibrium average value that you have of O at an energy E itself. So you can write down a long time average of any quantity you want to think about as what you have in equilibrium weighted by some probability distribution. Okay? And you could do this also more involved if you have, thank you, if you have a density matrix and so on. The same idea, of course, will apply there. So now you can actually, and as I should mention, of course, that all these averages that I alluded to earlier, all these that I have here, and if I have additional quantum numbers and so on, they're all in the end classical. So even though I put in the h bar, in the end, h bar disappears. So I had an h bar here, but because this enforced the delta function, this becomes a delta function in the end. The final answer I had here had absolutely no reminiscence of h bar. There's no h bar that appears in the final answer. Here there's no h bar. It's basically like a classical average. So a long time average is that I would have in equilibrium multiplied by weights, and there's no h bar. So it's sort of quite intuitive, of course. It's not terribly surprising. So now let's calculate the viscosity. And let's not do this usually in the conventional way using the Kubler formalism and so on. Let's just do it in a much simpler way. So let's imagine how we actually measure it. When you measure viscosity, there are many ways of measuring viscosity, but one of the oldest ways of measuring viscosity is taking a bucket or whatever you actually have with a fluid that you want to measure its viscosity. Take a sphere of radius r, plunge it into this bucket, and measure its terminal velocity. Terminal velocity, by Stokes' law, is equal to some constants, okay? This is just the radius that you have of your sphere and so on, this acceleration of free fall, difference of densities and so on, divided crucially by viscosity itself. So if you know the terminal velocity, if you know the long-term average of velocity, you can infer from that with viscosity. That's the oldest way of actually measuring, one of the oldest ways of measuring viscosity itself. So what we'll do right now is we'll actually calculate what this long-term average is, and from that infer what the viscosity is and get a prediction. Okay, and we'll measure and we'll calculate this average by just using the equation I just derived for you earlier, this trivial equation I derived for you, in which I wrote down the long-term average of the velocity of any quantity as what I have for velocity in equilibrium at energy E, meaning at temperature T corresponding to a particular energy density E itself, and multiply with probability distribution. Okay, so this I know from measurements. I can measure it in equilibrium what the terminal velocity is of a sphere falling down in the bucket at a temperature T or energy E, and I can multiply that by this probability distribution, do an integral and get the answer. Once I have this, I can plug that in here and calculate the viscosity. Okay? So everything is known, so to speak. The only thing that's unknown here, so far I'm not cheating. This is a general expression. The only thing that's not known here is, of course, is this distribution, this function Pt of E. And of course, the function contains an infinite number of parameters, of course. So you might say you can always fit any quantity you want to fit to this form, because of course you can always design a function pt of e that will do the job. That's not terribly surprising. So what we'll try to do is actually try to find out what's the most natural functional form that we'll have for this distribution. What should I plug in here for this distribution I have pt of e? So to that end, we'll just use simple principles. So as you know, in equilibrium, if I write down the probability of attaining a particular energy density E prime, it corresponds to a Gaussian whose width is set by heat capacity itself, heat capacity constant volume, times temperature squared. So it's basically proportional, the standard deviation is proportional to the temperature times the square root of n being system size, because of course heat capacity, of course, is extensive quantity. So here in the conventional case, think about the width for my distribution. That width, the standard deviation, divided by energy scale, that goes to 0 in the Thermodynamic limit. I have 1/squared of n fluctuations. The energy density is a very well-defined quantity, of course. Now, in our case, that obviously cannot happen. Because if it would happen, we would just regain the usual results of equilibrium physical mechanics. And we don't. What you actually measure in the supercooled fluid is not what you actually get in equilibrium. So obviously, this distribution cannot hold anymore. So what we should do is we actually should try to maximize the Shannon entropy, written here, for a probability distribution, and ask ourselves, what's the most likely probability distribution that we'll have here, pt of e prime, that maximizes the entropy, okay, with a condition that has a fixed variance. The variance cannot be 0, because if the variance were 0, I would just get, as I just mentioned now, I would just rederive what I had in equilibrium, and obviously the results I get should be different from equilibrium. So I should have a finite width sigma, and I should just maximize this entropy. And of course, as you know, or you can just do some calculation from the Lagrange multipliers, if you want to maximize the entropy with a constraint and a fixed variance, what you get is a Gaussian. Okay? So we'll have some Gaussian who's centered about what you have at temperature T itself, internal energy at temperature T itself, with some finite distribution. Now we can take this functional form of the Gaussian, thank you, and we can plug it in back into this form I just told you about earlier. We can plug it in this equation here. Here, it's the top line that you can see here, this integral. We can do an integral and find out the result. Okay, and that's what's schematically sketched here. So we can just plug that in and do the integral. And of course, this integral for a Gaussian is trivial. It's an error function, complementary area function. So the prediction would be, using these considerations, that the viscosity at temperature T for a supercooled fluid behaves as what I have at melting divided by this complementary area function of how far away I am from melting divided by temperature itself. Okay? And I converted the standard deviation itself divided by temperature scale with a dimensionless quantity. So basically, there's only one-dimensional scale. The width of the Gaussian is proportional to energy itself. Okay? So that's a prediction itself. That's how we derived in the first. Now I can, of course, check to see how this thing works, and it actually works pretty well. That's what I showed you at the beginning of the lecture. So now we can actually go and see how it works. So this is ultraphenol, one of these fluids that deviates most from Arrhenius behavior. Okay? This is raw data themselves. And you can fit quite well to this form with only one parameter. But of course, one fluid by itself is only one system. Not terribly surprising, you might say. So you can do this for all fluids which have literature in open data. Have data open literature. There's some data which are actually not published because they're proprietary. But all that are published, we try to fit them, and we got the same results. So basically, here are some metallic fluids and so on, other fluids, water. Okay, so all of them basically, they all collapse into this. They all work pretty well. And in fact, this works much better than this Vogel-Fulcher form. So this Vogel-Fulcher is this dashed curve here. The second one is VFT. It doesn't work very, very well. And you can do this for, here's a small sample of fluids. You can do it for more fluids. Okay. These are six fluids I showed at the beginning. So basically, it seems to work pretty well. This curve, the red line is this integral I showed you, this error function, one of its complementary area function. And all the other points are just raw data. Okay, and the only parameter in this problem is a bar, and it doesn't change that much, as I told you. varies from about 0.06 to 0.12, and it really doesn't change that much on average from fluid to fluid. And in fact, this quantity right here, this A bar, actually has physical meaning, because as you can sort of see from my earlier sketches, I assume they have some probability distribution, and A bar was the width of this distribution. So the larger the value of A bar is, the more influences of low energy states. You will feel them already at higher energies because their distribution is wider. So it starts to deviate from Arrhenius already at high temperatures. So basically, as I just alluded to now, the width that we have basically scales at 5 or 10% that I have of this Gaussian. And if I actually look at what I have for various, if I do simulations, for instance, and I try to see what happens at various temperatures, which is what we did here, you can sort of see that something starts to happen just above melting, and just above, actually, with this, it seems to coincide with this dimensionless parameter that I have now, but basically this parameter determining the width of this Gaussian. So if you just go a little bit above melting for this system, these here are these spanning clusters where you actually find these stable clusters. They start to appear exactly above melting. And the system starts to become rigid and so on above melting. So I guess I probably should stop here. Maybe I'll just say one more thing. I just alluded to it. I mean, so just as just jump to the very end of something I wanted to say earlier. I apologize for doing this. So you can actually go to the other extreme and ask what happens at very high temperatures. And there, of course, things typically behave in activated behavior. Well, I should just say, let me just tell you the punchline. The punchline basically is that if you try to fit it to an activated behavior, what you find is that, I apologize, what you find is that the pre-factor that you have seems to be nothing else but the number density of how many atoms you have per unit volume times Planck's constant. So the units of viscosity, as is well known, are equal to Planck's constant times the number density, 1 over volume. And it seems to be that if you try to fit the viscosity to an Arrhenius form, the pre-factor is nothing but just this average, this product, n times h. And if you try to look at the raw data themselves and ask how much do you deviate from that, for deviations, these are deviations from this raw value that you might expect, but on average, it seems to cancel. So on average, this pre-factor is pretty close to 1. So it's basically of order 0.6% of systems that we looked at. And the reasons might be reasons for this, but I don't have time to go over that. So at any rate, let me just tell you back. Let me just go. I apologize for this talk. I am not giving it in a good way. I sincerely apologize for this. But so let me just go back to what the conclusion, my conclusions. So the basic punchline I wanted to tell you is that this transition, even though it seems to be very, very different, might actually be a conventional transition in disguise, okay? Just because you just smear it out with a distribution, that's it. So it's a minimal change for what we usually know. And only the singularities that appear that you have are those of what you have for equilibrium systems. So the eigenstates themselves, they have singularities. When energy goes from above melting to below melting, that's manifest anything you actually would expand in terms of eigenstates, including what you have for a glassy system. And how you can actually test this. So here I just showed you what happens for the viscosity and the relaxation data, but you can of course ask yourself, well, the same distribution, this Gaussian distribution actually can describe everything. So there's only one parameter, this width of this Gaussian. Can you predict all data using only one parameter, what you have for all fluids? That we haven't done, partially because it's pretty hard to compare it to various things. But that's basically what I wanted to tell you.
two quick questions.
Yeah.
The first one is, what if you, instead of velocity, if you calculate something like an order parameter, then the states will be dominated by the states that have lower energy than your melting temperature, and then you might get some kind of order parameter in your calculation that's not present in the glass. So can you comment on that? And the second one is, sorry, I forgot my second question. If I think about it, I'll tell you.
Okay, so you're asking why is it not a crystal? So you're asking basically if I have a distribution which actually has crystalline states, why is it not a crystal? Which might seem like a paradox. So it's not a paradox in the following way. So suppose I look at any system, any state I want to think about. I can always expand that state in a complete set of eigenstates. So whatever, if it's an amorphous state, but it's at low energy, I can always expand the complete eigenbasis. And if only states are around at low energies are those of a crystal, there's no way around it. State an alternative difference is suppose I have different crystals with different wave numbers, Q. So I have different Bragg peaks that I have associated with it. But now suppose you superpose many states having Q's at different angles. The resulting state will not be necessarily ordered because you just superpose the various amplitudes actually just get mixed. You see what I'm trying to say? Oh, okay.
Normally when glass, you think of rare events.
Right.
Or just a Gaussian with
So,
no
so
rare
no,
events.
okay, the rare events are here. The rare events are just if I go to this cartoon I showed you earlier. So it's a very good question. I apologize, I didn't understand what you asked in the beginning. So if I go here, sorry, not here, here. So here's my distribution of low energies, low temperatures. So now you can see most of its weight corresponds to a solid type eigenstates. But you see it has a tail above melting, and that tail is narrow, but it's not zero. Because it's overall this tail is very, very narrow, the probability of being here is very low. So these are rare events. So it's very unlikely that you'll actually have energy above melting, but once in a while it does happen, and that enables flow. So in the fluid type states we have flow, in the solid type states we have no flow. It's very rarely we actually have this, but we do have it, and that's why we have flow. So the picture really is, as I go down in temperature or energy density, this thing goes down, this weight goes down. As a result, it becomes more static because the probability of motion just goes down. There's no singularity. This whole thing is continuous, but it just drifts downwards, and this tail becomes more and more narrow.
Yeah, thanks. This one slide called the viscosity experiments. That there is a white picture with a black dot and a right curve fitting. Would you able to find that slide? There's one slide titled viscosity experiment. That shows one figure.
Oh, but one I didn't show, one didn't talk about.
Yes, yes.
Yeah, okay, that's how we measure it, and not we, my colleagues measure it. Yeah, so actually the conventional way, as I told you, is to measure it with a sphere and using Stokes' law. But of course, this has been around for decades. Another way of measuring it is actually like this. So what you do, this one?
The next slide.
The next slide.
With the right curve fitting.
This one?
Oh, yes. If you rotate the picture 90 degree clockwise, and if you have more data point, maybe you see the plateaus.
Maybe I'll see what?
The plateau, the steps. The plateaus. If you rotate the pictures 90 degree clockwise.
Yes.
And then if you have more data points, then most probably you see the plateaus. And these plateaus increase, follow the Faro tree. And this is called a devil's staircase.
It's called what?
Devil's staircase.
Devil's staircase. Yeah. Oh, okay.
Is this
okay, I'm sorry. Yeah, this is probably not devil's staircase. But it's a very good question. So, of course, you would like to know, these are raw values that we have my colleagues have from our measurements, and we try to fit the viscosity measurements to this simple expression for the theory to see how it works. Yeah.
So, I was just curious, why this kind of plateaus just come into presence in these kind of things?
Why do they present like this?
Yes, and also, they seem to me a fraction number, and then it's follow the devil's staircase. So if you measure the values of these kind of things, then you'll find the fraction numbers.
Right, of course. So the problem really is, so you want to see that the number is close to 1. The problem is the data set that you have is not very large. In here we have 23 different fluids. So if you do a histogram, it will be useless because you just have bars which are 1 or 0, and it's hard to say. So we do here is we wrote down the integral that you have of a probability, some of the probabilities of being smaller than something, okay? So now it becomes continuous. So instead of a histogram, now you just spin you sum histogram. So it becomes more continuous. And now you see if you have a Gaussian distribution, what it would actually be. So if you have Gaussian distribution of overall average value, where you have of 0 relative to what you expect, what you actually get. So this red curve is what you have from if you just use the variance that you actually measure from raw data, and you see write down the corresponding normal distribution and do integrate to find the error function, and compare it to actually the probability from different data points that you actually have. But overall, the value of S is smaller than something.
Okay, thanks.
I'm not sure if I answered the question. Yeah, so the problem is there's not enough data to actually do. If you just do histogram, it would be useless because you just have just be a bunch of steps. So you just sum it up. Okay, so you ask, in what fractional instance is a prefactor smaller than something? And that's what we've done here.
Okay, thanks.